Okay, hello, sorry, I'm very sorry. I thought it starts 10 minutes later. So I'm usually not using this early slot. So give me a second to start up the whiteboard, etc. One of you has asked me about the video recordings of the seminars. Unfortunately, I was busy the entire day yesterday and today, but I will look into this. There is a slight problem that our conference is not under my account, but under the study office. So maybe I won't be able to do this, but I will have to ask them. So it might take some time. Here is the link for the whiteboard, and here is the demonstration of the whiteboard. And so let me check my notes. I think we're kind of ready to begin. Okay, so if there are any questions before we start, please tell me. Otherwise, we shall start. Okay, no immediate questions. I'm sorry, I have a question. Give me one more second to check the key. Here it is. So I have some magical key I need to input. Here it works. Okay, so now let me move to this. Okay, so, well, the bad news are that there was nothing new on the lecture. The last lecture was devoted to the same topic. Well, the same topic as in big topic determinants. That's not very surprising because the next lecture is also on determinants. That's a huge topic. But moreover, the last lecture was devoted to proofs about elementary operations, and we already discussed elementary operations with determinants. So this means we have kind of a problematic situation that, well, there is nothing to cover. But first of all, there is a small problem I want to introduce about one topic that was on the lecture. And second, well, we're going to slightly go ahead and discuss the next topic, the next, how to say, tool, how to compute determinants in yet another way, because the next lecture will contain several subtopics simultaneously, well, not sequentially. And well, so basically we are going to split the topics from the next lecture into two seminars, this one and next one. Okay, I hope this makes sense. So before we do so, let me remind you one particular theorem from the lecture. There is a theorem that states that the determinant of a product of two matrices is equal to the product of the corresponding determinants. Very simple and easy to memorize. There was some elaborate proof using reduced row echelon form, a very interesting proof, because in many books you will find other proofs, not this one. But still, that's fine. So there is such a theorem. So it is mainly used in like technical stuff, in like proofs of other theorems, etc., etc. We are going to see it many times during the course. But it's not like there are some problems that may be solved with it, right? Because, well, I mean, it's hard to imagine a problem where you have some A and B, and for some reason you want to find this or something. So it's very hard to invent a problem about this. However, one such problem exists. Well, not really one, but several, but still. There are several problems about this, and all of them look crazy and, well, very interesting. So let me showcase one such problem. Please note that it is kind of an advanced problem. It is fine to see that something magical happens. My main goal right now is to show something beautiful, not to show something that is like a key problem or something. It is not a key problem. It is not like a problem from a series of problems. It is just one separate problem that shows that this topic is kind of beautiful. Okay, so enough of talk. Let me finally introduce an interesting matrix. Give me a second to check myself because it's not really obvious, but it's correct. Okay, very good. So consider, please, this matrix. We wish to find its determinant. So we may obviously do this by the definition of determinant, but we will have then 24 summands. That's a lot. Moreover, the textbook has a similar problem for the 8 by 8 case, where there are too many summands. Likewise, we may do elimination method. However, elimination in 4 by 4 case with many parameters will also be kind of problematic, right? We will have to like do many steps, and on each of them there will be some conditions that something is non-zero, and that will be very frustrating. Moreover, if even we for some reason ignore those conditions and consider only the general case where everything is non-zero, everything that we require as middle steps, still it won't be easy. You will have some huge expressions. So, well, there is a third way that is called expansion by a row, which we are going to discuss today later, but you will see that it also doesn't really help in this exercise. So nothing helps. However, someone noticed that if you multiply this matrix by its transpose, lots of magic happens. So let's look. Let me maybe first write down them next to each other. And then let me multiply. So this row by this column gives a squared plus b squared plus c squared plus d squared, right? Well, okay, that's fine. So the problem is that if in each of 16 cells we obtain some expression like this, our task becomes harder, not easier. However, in fact, we don't. Let's look at the next one. It is very interesting. So I take this row with this column. Please look carefully. So A gets multiplied by minus B, and B gets multiplied by plus A, and they cancel. Similarly, CD minus DC cancels. So the next cell is 0. This is a small miracle. Sorry, yeah?
Is it because the matrix A is a skew symmetric matrix?
That's very good that everyone asks this question. And the answer is no. I can give examples of many different skew-symmetric matrices where this doesn't work. So no. No, this works. There is some property of the matrix A that I could mention. It is called orthogonal matrix. But it is not orthogonal, but it's almost orthogonal, which we will discuss later in the course in spring. Everything interesting happens in spring. However, it's not obvious. And certainly we don't know it at this moment. So at this moment, well, it just so happens that A is some special matrix so that something miraculous happens again. It's very hard to invent this trick. Somehow someone guessed to consider this matrix and we obtained 0. And moreover, in the next cell, here we have minus CA, but here we have CA, it cancels. Minus BD and plus BD, it cancels. And similarly, I may compute all the cells and there will be many zeros. In this cell, in the second row with second column, minus B times minus B is plus B squared. So if you compute, you obtain the same expression. And here, you again obtain zeros. And similarly, one may compute all the cells. I won't give details about each cell because it's like computations, everyone is able to check them. Now, so how someone guessed to consider this matrix again is highly unobvious. We will see some details in spring when we discuss orthogonal matrices. However, my question right now is much more easier how to use this fact. So we proved something about matrix A that this equals a very beautiful matrix. How to, this is in fact A squared plus B squared plus C squared plus D squared times identity. So how to use this fact to compute the determinant? Free microphone.
We need to use like the thing that you wrote in the first line.
Obviously, yes, but how to use it?
It's A transposed the determinant multiplied by A determinant multiplied by A transposed determinant is
Okay, this is true. So what?
And this determinant equals that thing in the diagonal in the power 4.
Very good. In the power of 4. Why?
Because all other elements are zeros.
Okay, sure. This determinant simply equals the product of the elements on the diagonal. That's the 4th power. Okay, but how does it help? So we found not the determinant we were looking for, but its product with something else. How to move from here? So now we want to.
Would they be these determinants equal just because this is a transpose?
You're right. Lucky for us, determinant of the transposed matrix is the same as the original one. So this is simply the square of
Can we reduce power?
Yeah, so we can, if we know that this equals this, then this equals either plus this expression or minus, and it is easy to see that it is plus. I'm sorry, squared. As it contains a to the 4th power, it is with plus. You can see a to the fourth power from the diagonal of the original matrix. That's it.
I have a question. Can you explain? We get a multiplicated a transposed is identity matrix, yes?
No, it is proportional to the identity matrix. It is identity matrix times something.
Oh, okay, okay, thanks.
It has some number on the diagonal here. And so maybe I don't hear any questions right now, but there was an important question in the other group, which I want to like emphasize, because maybe it will arise later. Someone said, looking at this formula, wait, why isn't the answer this number? This matrix has determinant 1, and we multiply this matrix by this number. Shouldn't the determinant also get multiplied by this number? And the answer is no. There is no such rule. That's life. There is no rule. So it is not true that determinant of lambda times some matrix equals lambda times determinant. In fact, what is true is determinant of lambda times some matrix equals let's think.
Determinant of A multiplied by lambda in the power of, I don't know how to say, what, of size?
Yes, of the size of the matrix A. A is a square matrix, otherwise the determinant doesn't exist at all. So it has some size n by n. So, well, if I were writing some formal text, it would be better to say what is n before I'm writing this. But in this context, it's easy to understand that I mean the size of the matrix. So in fact, it gets multiplied by lambda to the nth power because we don't have this rule, but we have the rule for extracting a number from a row. The D operation allows to divide a row of this matrix, to divide one row of this matrix by lambda and extract this factor outside. Then I divide the second row by lambda, then the third row, etc. After I divide n rows, lambda A turns back into the original matrix A, and outside I obtain lambda to the nth power. Okay. Are there any further questions right now? If so, let me now switch to, wait a second. I'm sorry. Let me now switch to the next topic. So I'm going to briefly introduce some definitions, which are going to be repeated in the next lecture, but with more detail. So it goes as follows. Suppose one has some matrix A. So let me consider some particular element Ij, okay? And I'm going to perform a strange procedure. I'm going to take its row and its column and throw them away from the matrix. I consider now the same matrix without one row and without one column. I'm sorry, it is not I, but J, right? So I throw away J's column and I throw away ith row. So here is I minus 1, 1, and it is I minus 1, 2, etc. And so the next is not ith, but I plus first. Okay. Any questions? It is an easy concept, I hope. Throw away something and something. Okay. So this matrix, well, is not important by itself, but what is important is its determinant. Well, no, wait a second. So this matrix by itself, the lecturer has a notation which is slightly strange, but still fine. He denotes it like this: A with indices in around braces, not braces, parentheses. And here we have I and J separated by a line. Okay, whatever. This notation means this matrix, okay? Throw away ith row and jth column. And what we are interested in is the determinant of this matrix. So let me denote it as Aij. This determinant has a special name. It is called ijth minor of A. In Russian, it is called minor matrix. Okay. This is not the only thing called minor. I mean, when you throw away several rows and the same number of columns, so that the result is still square, this is also called a minor. For example, you can throw n-1 rows and n-1 column, and only one element will remain. That's also a minor of the original matrix. But we're going to concentrate on this kind of minors of size n-1 by n-1 because we're going to need them today. So is the definition clear? Are there any questions?
So we call the minor the changed version of our matrix when we remove I and J?
No, not the, that's not very important, but still technically not the matrix itself, but the determinant, the result. Okay, the
Of
matrix
this
itself,
changed
we are not
matrix.
interested in it. Sorry?
Yes. So the determinant of this changed matrix, yes? I
Yes,
see.
the determinant of
Okay.
the matrix after throwing out one row, one column.
Okay, thank you.
Very good. Any other questions, anyone? Everything clear? Then let me produce a wonderful formula that is strange but beautiful. That is a third way of finding the determinant. As I said in the beginning, we know how to find determinants by definition. We know how to find determinants by Gaussian elimination. Here is a third method. It goes as follows. We take the first element in the first row and we take its minor, this number, and we multiply them. Okay, why not? Then we take the second element. I leave a white space here. I will fill it in a moment. And we take its minor and we multiply them. And then we take the third element and its minor, etc., until the final one. And this way we go through the entire row. So there is a theorem, again, it will be proved in the next lecture, that this minus this plus this minus something else, etc., plus minus 1 to the power of n plus 1, or n minus 1 if you wish, equals the determinant. let me illustrate this in the 3x3 case. In the 3x3 case, this formula gives A11 times this part. This is what remains if I cross out the first row and first column containing this element. This part remains. Minus the second element in the row times the following determinant. This, 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 and this. I cross out the first row in the second column that corresponds to the second element. So what remains is 2 elements to the left and 2 elements to the right. And finally, A13 times the remaining block. This one, the bottom left block. So to check that this is indeed correct, I may find those values by definition of the determinant. And you may compare this to the expression we obtained last time to see that indeed it is the same expression. Of course, this doesn't prove anything. I mean, well, it proves that this formula works for 3x3 case, but not the arbitrary case. Again, the proof of the formula will be given in the lecture. So this is called expansion of the determinant of the determinant. Too many letters. By the first row. We picked the first row and we went through it, and for each element of the first row we have written something. Okay, before I continue, are there any questions?
So, can you again explain the algorithm, how we throw the rows?
Throw away?
Yes.
So again, for some element, for example, for the second one, okay, it is kind of in the middle. For this element A12, when we consider the, let me copy this maybe and like paste somewhere here and use colors. So when I consider this element, the minor that corresponds to this element is like this. I take this element and I like cross out its row and its column. What remains, for some reason here, the indices disappeared. What remains is this part and this part. So together they form the following minor of smaller size.
Okay, thanks.
Very good. Is it more clear now, I hope?
So we go from the right to the left in that case.
I'm sorry, what do you mean from why from the right to the left?
We just take as the last column, the first A23, A33.
No.
And then
No, they are in the original order.
I get that this A23, A33 column is just also the last column in this determinant, but we just, in the first case, when we multiplied it by A11, we took the second column. So we just, in that case, let me determine.
Sorry. So again, in the first case, okay, so in the first one, we were considering this element, so we threw out this row and this column, and we took the rest. What remains? And here, this part remains. And when we consider the third one, so the left part remains.
Oh, I see.
Mhm.
Okay, thank you.
Okay,
Yeah, I think I've got it.
okay, everyone, no more questions? Please think, because I'm going to move otherwise. So, well, then, what looks slightly weird in this formula is that we use, for some reason, the first row. Is it like the magical row or something? No, there is a similar formula for any row. Let's look. There is a slight difference. So let me first write it. The formula goes as follows. Now, so again, in some arbitrary row, in ith row, we take the same. We take the first element of the row and its minor. We take the second. I'm not writing signs yet. I will write them in a moment. So I leave some space for them. We take the second element of the row and its minor, the result of crossing out the ith row and second column here, etc., until the last, which is, well, nth element of this row and its minor. But the signs are not the same now, not plus minus, but instead they're as follows: -1 to the power of I plus 1, -1 to the power of I plus 2, etc., until -1 to the power of I plus n. So basically, they also are changing each step. They're also plus minus, but the start depends on the row. For some rows, it starts with plus, and for some rows, it starts with minus. Again, that's life. That's how the formula works. You will see the proof in the lecture.
So when we multiplied it by the negative and then we do the by the positive.
Again, you can check by using this formula. You find I plus 1 and you will see it depends on the number I.
I see. Okay.
For example, for the second row, where I is 2, then this will be minus. So it will start with minus, then will be plus, etc. And there is an easier way to remember this. I can simply, I'm sorry, let me finish and then maybe the question will disappear. I can simply use the following rule. For the first row, it is plus, minus, etc. For the second, it is minus, plus, etc. For the third, it is like this, etc. So if we simply take this rule and draw it, we can immediately see like a law that it follows. It is the chessboard pattern. It is simply colored as the chessboard. Like the chessboard is white, black, etc. Here it is plus, minus, etc. This allows, yeah, okay.
Yeah, sorry.
This answered the questions, right?
Yeah, I just suppose that this is also because happens of our power. If it's becomes 7.
Yes, this is the way how to remember those powers. You can either compute the powers or simply look at this picture and you see those powers.
Okay, I've got it. Thank you.
Very good. So now we have this formula, we have everything we could practice, but one more small technical thing before we go to problems is that sometimes people don't like those -1s everywhere. So instead they introduce one more thing, one more, I don't know how to say, object, which your lecturer denotes in this huge way, but still, it is the same as the minor ij, but multiplied by this number, -1 to the power of I plus j. This, well, object, this number, is called cofactor of A. ijth cofactor of matrix A. Okay. In Russian, if someone is wondering, cofactor is алгебраическое дополнение. It's not very obvious how to translate this. That's why I wish to write this. Алгебраическое дополнение. Okay, so this is the cofactor of ij's element. And using cofactors, I may write that formula in a more compact way. Now, the formula above says that when we expand through the ith row, we get the sum for each element of the row, for each j in the row, we get the element ij's multiplied by the cofactor ij's. This formula is the same as the formula above, only I took all those -1s and placed them inside this factor. Okay. Now, let's practice. So give me a second. How do I open this? I wonder. Okay, give me several seconds. Wait, what? I'm sorry, something doesn't work. So here is an example that we had last time. We have already solved it with two methods, as far as I remember, using the definition by straightforwardly writing 6 summands and using Gaussian elimination, simply transforming this matrix to the triangular form. Let me do this problem third time using this formula. So if I select some row, for example, the first row, and expand, the result is as follows. For the first element, I cross out this row and this column. What remains is this part. So I write it down. For the second element, I have minus because of the chessboard pattern. This is plus and this is minus. -1 times some determinant. To find the determinant, I cross out the row, I cross out the column, and what remains is this part and this part. So let me write down this part and this part. Finally, for the last element in the row, the sign is plus, yes, plus, minus, plus. And after crossing out, what remains is the left part, this part. So let me write it down. And I may compute. This one is 9 minus 8. That's 1. This one is 15 minus 2. That's 13. This one is 20 minus 3. That's 17. So what remains is to compute the sum. Yes, do ask.
Isn't it 71?
3 times 6, 17. No, it's 51.
Oh.
30 plus 21. No. And in fact, 40 is what we got last time using 2 other methods. Any other questions? Don't hesitate if you have questions. Okay, then let me upgrade the problem. So before I do this, so in this problem, we see that the method is quite easy to use in 3x3 case, but not like it's not like it is easier or harder than the previous two methods. The problem itself is very easy, so all three methods give results easily. And you may see that this method, well, is kind of useless in 2x2 case because 2x2 case is already easy. You simply use the definition. And in 4, 5, etc. case, it is also kind of hard. It is easier to use elimination usually. So you basically you turn one big determinant into smaller ones. That's good. But there are many of them. That's bad. So why do we need this method? Let me provide an example where it looks useful. Let's look at this matrix. Here, it's not nice to use the definition because there are 24 summands. That's slightly too much. And it is not nice to use elimination because we have letters. They're always an abstraction to this. And so instead, let us somehow use expansion. Which kind of expansion do you recommend? That's an easy question, but still.
For the third row?
Obviously, that's for the third row. Thank you. We use this row because it kind of looks differently. And if you cross it out, what remains doesn't have letters. So I write the following. It equals this minus this. So how did I obtain this? I crossed out the first column and third row. What remains is this part and this part. I have written them here. Now, this, and this. So the question is how to find now 4 determinants of size 3x3. Unfortunately, I don't have any magical method that would allow me to do this easily. So this problem requires some time spent for the computations, unfortunately. So we may use elimination. And as far as I remember, it's nice before doing anything to subtract this row from this row in all 4 determinants. So let's do it. There are many different ways we could do with those determinants. Many different actions we could do. But this one, well, is like the same in everything, so that's always nice. So what we obtain is this, sorry, not plus, but minus. This. This. And this. Please think whether you have any questions at this moment.
Why? The determinant which you multiplied by b, why do you have in the third row -1, 1, 1, not -1, -1, -1?
So 3 minus 4 is -1. -1 minus -2 is, I'm sorry.
by C.
Ah, that's the wrong one. No, it's still correct. 3 minus 4 is -1. 4 minus 3 is +1. 3 minus 2 is +1.
Can you remind what operation turns all determinant to minus? On the previous seminar, we were talking about it.
Yeah.
And,
Yeah. I got your
forgot.
question. Yes. When we swap the places of two rows, the determinant becomes minus the previous one. That's what you were, I think.
Oh, okay, thanks.
I'm sorry, but I think
Yeah.
that Arina meant the C1.
Okay, that's C1. Let's
There
check.
should be -1.
The first one should be -1. Okay, sorry, I didn't get it. Sorry, you're right. That makes sense. Okay. So now we can use last row to simplify other rows, or we can use columns. Look, we can do some actions with columns to make some of those ones into zeros. And I like this idea. So maybe it's not the best, but today I really like it. So let's use it because it will allow me to showcase one more part of this method. Again, I don't claim this is the best move, but this move will help me to show another idea. So let's do it quickly. So in the first one, the second row after the second column after subtracting the first column, okay, I subtract the first column from the second. What I get is 7, 4 minus -3, 5, 3 minus -2, and 0, 1 minus 1. Here I have 4, 4, and 0. Now in the next one, I obtain, so the first column stays, and the next one is, now I add the columns. So the next is 6, 7, 0, and this one is 3, 6, 0. For C, again, the first column stays, and the second one becomes -1, 2, 0, and this one 3, 6, 0. And finally for G, I'm sorry, not plus, minus. So that's -1, 2, 0, 6, 7, 0.
And we
And
can use this operation only on determinants, yes?
with columns, yes.
With columns, yes.
Yes, we know that the determinant, that elementary operations for the determinants may be used both on rows and on columns. The proof of this was as follows. The determinant of the transposed matrix is the same as of the original one. Thus, the operations are the same.
Okay, thanks.
And that's very useful. We discussed last time that it is often useful to do like some operations with rows, then switch, and do some operations with columns, then switch, and so on. It is often very nice.
Sorry,
Yeah.
but isn't it where A, the last column, -2, 0, and 2?
This one?
Yes.
4.
No, it's D.
Sorry. 1 minus 3. 1 minus -3 is 4.
Okay, thank you.
It's correct. So now I got some zeros inside. That's always good. I could rearrange the rows in different order and try to make everything like, well, triangular. But instead, I can kind of do the same using this new method. I can do equivalent things in a more easy to write way. What I do is I expand this matrix by the third row. if I do this, I obtain the following. For this element, I obtain 1 multiplied by this smaller minor. And for the other elements, I obtain zeros. I don't need to write any minors because they don't matter. When I multiply 0 by something, I get 0, as far as I know. This gives me a very important rule. When I have a row or a column with many zeros, I may immediately expand, not waiting for something to become triangular or something. I can expand and make the size of the determinant immediately smaller. Very helpful trick. Similarly, for the second one, I may write that it equals this -1 times this determinant. Third one is -1 times this determinant. And the fourth one is -1 times this determinant. Are there any questions for the move I did between those rows? So what remains is, well, a question of some simple computations. 28 minus 20 is 8. 36 minus 21 is something, 15. And here is a minus, and here is another minus, so it's plus 15. -6 minus 6 is -12. And here we have a -1, so -12 with this is plus 12. -7 minus 12 is -19. And we have 2 more minuses, so altogether it is -19. This part is not very interesting. Okay. So think for a second if you have some final question. Otherwise, let me move to a final problem for today. So the last problem is kind of much harder than the previous ones, but still important in our course. So let's go. And maybe let me skip this frame because we have something under it written and go to the right like this. Okay. So here is a determinant. That is huge and very interesting. So the first column is the first variable x1 in all the, well, all different powers, the zeros power, the first power, the second power, the third power, etc. until n minus first. The second column is the same, but with x2, with the second variable. The last column is, well, the same for the nth variable. So we have n different variables. And the question is, what is the value of this determinant? This is a hard question. Obviously, it's extremely hard to find this by definition. I wouldn't even try. And so we have to use the remaining two methods we have. Elimination, we want to use some operations on rows and columns, and expansion by a row. In fact, we will use both. Moreover, there are still many ways how to go. So is there any obvious idea for you what can be tried? something obvious. I promise I won't judge you yet.
Maybe to try from the last row subtract the upper ones.
Well, then we obtain, so if, for example, from this row, you subtract this, you get expressions like x1 squared minus x1, and it is like worse than the original x1 squared.
Maybe we can do the row operations L when we multiply
Which one?
row
Yeah.
by something and subtract.
Something is very interesting, but without any.
I suppose that that can look awful, but we can just try x1 in the power n minus 1 and then just here subtract. Then this x1 in the power n minus 1 get from the so from the brackets, and then just these brackets inside the sum, right, like with the via sigma symbol.
Okay, I'm sorry, but again, what
But-
is the idea that you, I didn't get what you want to do. Divide this row by x1 to this power,
No,
then we
I
will have
just-
many fractions.
I've said before that this from this last column subtract the others.
From the last column.
Yes.
I'm sorry, I thought about the row. From the last column, subtract
Ah.
others. Then you will have difference of powers, right? That's an interesting idea. So, and different people suggested this idea in different ways. I will use a similar but slightly different idea. They are very similar. We will see in a moment. We can, for example, take one fixed column and subtract from all the others. The good part is that this one disappears. We get many zeros. So let's look carefully what happens if I do it like this. Again, unfortunately, I claim that unfortunately we will have something bad happen soon, but still let's first try and then analyze the result. So the good part is that we have zeros here. And what we have here is not very bad. This one is difference of squares. That's okay. Then we have difference of cubes. It's okay, etc., until here we have difference of n minus first powers. And in case someone doesn't know, there is a formula for the difference of case powers. Suddenly it stopped working. We recommend that you wait. Okay, I waited. Do you hear me? Is everything well?
Yes.
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 Very good. Thank you. Then there is the formula for the difference of case powers that works as follows. Like this. So in the last column, I obtain xn minus x1, xn squared minus x1 squared until the remaining one. And so this thing may be simplified by two ideas. First, when I see a row full of zeros, I immediately expand. This is like, you know, like a reflex, okay? As soon as I see a row with many zeros and one non-zero element, I always expand. So after doing this, I will simply get the part of this matrix, this part. So let me copy it. Okay. Okay, it always copies with some problems, but let me make it better. And now I need to somehow, well, find out this part. But Well, the idea is that this column, by this formula, everything in this column is divisible by x2 minus x1. So I can divide, and what I get is as follows. So after this, I may do this. So I can do this with one column. I can do the same with second column, third column, with all columns. And this way, I kind of take many factors outside from this determinant. So the determinant kind of becomes easier, but not really. Unfortunately, this expression is very huge and not very nice to work with. And that's the problem. This way is kind of nice, but unfortunately it doesn't work really well. I don't recommend it. So with heavy, it can be finished. This computation may be finished theoretically, but it's not so easy to do so. So instead, I recommend to go backwards. To go backwards to the very beginning. And let's start once again. And we don't have much time, so let me provide the idea myself, because we really don't have much time. The idea is to do something similar to, to the usual move of elimination, to use the first row on the second row with coefficient x1 so that this x1 vanishes, and to use this row on this row with coefficient x1 so that this x1 square vanishes, and the same for each row. Again, I could instead use the first row everywhere, right? I could use, for example, for the third row, I could subtract the first with coefficient x1 squared. This is a more logical move. But it doesn't work well. If I do like this, I will obtain something similar to the previous case. However, if I do it like this, you will see in a moment that everything cancels out much better for some reason. It's very hard to, how someone guessed to do exactly this, not this. I don't know. But
I suppose that's just because the difference, if we multiply, we can, just because one has a really good property. Just because if we multiply it, we will get the number itself. So we can just multiply in the first row by x1 and whatever number which we like, and then use this for each next
yes, but
row.
I'm exactly saying that it's a bad idea to use the first row for some.
No, I mean that this is the first row we multiply by the x1, and then we see that the that's only difference between the rows, only this x1. So we can, this is the power. Our main problem is the power. So we go after that, and we just remember that, yes, we have an operation of this is the second elementary operation we use. The first, yes. And this is not forbidden for us to multiply.
Yeah, sure, but okay. I was talking about, again, how we guessed that this idea is better than the previous two. And so, well, definitely it's not forbidden, but how to guess to use exactly this idea? There are like millions of other competing ideas, but why exactly this one? But again, let me finish what happens and quickly compute. We don't have much time. Yes?
I suppose this is just because of the power. The power is just the same as multiplication by the same number multiplies by itself several times. So I guess this goes from this idea.
Yeah, that explains why we use this to like make this part zeros. But okay, but now, so this doesn't look much better than the original one. But I claim it is better because after I expand by the first column, I obtain the following. In this expression, I may take x2 minus x1 outside. In this expression, I may take x2 minus x1 outside, etc. In this expression, I may take x2 minus x1 outside. And what is good is that the thing that when I divide by this, and I'm going to divide by this in the next step, the thing that remains is easy. The thing that remains is not this huge expression from the previous time, but this short expression. So let me divide the second column by x2 minus x1, the third column by x3 minus x1, etc. The nth column, the last column by x2 xn minus x1. Then what remains is as follows. It's hard to fit everything on the screen, but still, when I divide this by this, I obtain x2. The next one becomes x2 squared, etc. until x2 to the n minus second power. And the same for the other columns. And so I obtain the determinant that, well, maybe is not very easy to compute, but it looks the same as the determinant we started with. Only it is smaller. What is the magical word that immediately we want to use?
We can do same operations. So in our multiplication.
Okay, we can repeat the process. We can say we do this again and again, etc. And if we are pedantic enough, we can say we use induction. And so after many iterations, after many steps, we will obtain the following wonderful formula, that the resulting determinant is equal to this product times the same product, but here everything is minus x1. Next, we will have everything minus x2. But that's not the end. Then we will have everything minus x3, then x4, etc., 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 until xn minus 1. So for each pair of variables, there is one variable minus another variable. There is a short way to write this down. Like for sum of many, many things, we use capital letter sigma. It stands for the sum. Here we use the capital letter pi. This is a Greek letter, so you know small pi. Okay, this is capital pi. We know it from the Russian alphabet, obviously, because Kirill and Methody took capital Greek letters and used them. If you look somewhere into a copy of Greek alphabet into capital letters, you will see that you know most of them. You know letters like alpha capital or beta capital or gamma capital, you know them. And this is pi capital. So still, this means the product of all such possible things, or again, if you are pedantic enough, I goes from 1 to n and j goes from I plus 1 to n. So it is like a double cycle. We go in a double cycle through those indices and multiply all the results. Questions? Okay, so this way from this place to this place was very long and with many details. You are not expected to memorize it or something yet. I'm sorry, that's a stupid joke. But what you are expected to remember is the result. The result that the original determinant equals this formula, because we will use this result. And let me say that this determinant has a name. It is called Vandermonde matrix or Vandermonde determinant. This is obviously a family name of some person who lived many years ago. And you're going to have a bit of discussion on the same determinant in the lecture. So I hope that a repetition of this will help you memorize it better. You will meet this determinant later in some problems. Okay. Once again, let me ask if there are any questions. And if no, we have to stop. The time is limiting us. Okay. So see you after the break. We have a small break for 1 week. And well, then we meet once again. I hope that offline, but who knows?
Thank you very much. Bye.
Okay,
Thank you
thank
very
you.
much.
Thank
Goodbye.
you.
Thank you. Bye.
Seminar. Goodbye.
Thank you. Goodbye. Goodbye. Thank you.